it's periodic. Only thing is, what happens is, the system, once you start it from some initial condition, it will asymptotically approach a loop, and after that it is completely periodic. So it will approach a solution where xt is equal to x of t plus capital T, where capital T is a period, right, of the system. So this is an illustration of how a limit cycle looks like. So suppose I start from this point, right? I move around and gradually approach the solid loop, okay, which is a cycle, which is called a limit cycle. It's a cycle that is a limit, right, of this trajectory. So you start anywhere and you're in the limit, you slowly approach the trajectory. It is as though you're falling into a well, but only thing is it's not a point, but it's a loop, it's a cycle. Okay, so here again there are several variations. In a stable limit cycle, if you start from outside, you slowly get attracted inwards, you flow inwards and get attracted towards this loop. And once you reach the loop, you'll keep on going round and round the loop. The loop doesn't have to be a circle. It can be any in a complicated shape. It cannot cross over itself, right? But it can be any complicated shape. So similarly, if you start from inside the loop, right, because it is a two-dimensional thing, there is a concept of inside and outside when you have a loop. So if you start from inside the loop, you go around and after some time you tend towards this loop. And once you reach the loop, you go round and round the loop. That reaching happens asymptotically. So ideally it takes infinite time, but you can get very close to the loop quickly. So when you start from both outside or inside, if you reach the loop and stay on it, then you call it a stable limit cycle. Okay, this is just like a stable node. In case of stable node, you go to a point. In case of a stable limit cycle, you go towards a cycle, towards a loop. Therefore, just like you have an unstable node, you also have an unstable limit cycle, where if you are on the loop, you start on the loop, you keep on going on the loop forever. But by chance, if you get perturbed and if you get kicked off the loop, if you get kicked to the inner side, then you'll go around, you'll go and typically tend towards a point, and that point will be typically a stable focus. You know, in a focus, you spiral around a point and then end up there. And if you get kicked off the loop in the outward direction, then you go around and you move away from there. What happens after, you know, when you go very far, we don't know, because that depends upon the global structure of the dynamical system. But just like in case of an unstable node, if you get kicked off the node, you move away from the node. In case of an unstable limit cycle, you get kicked off the loop, you move away from the loop. You don't come back to the loop. Now there is also something called a half stable limit cycle, where on one side you can get attracted, other side you can get repelled. Okay, so you start from outside, you get attracted towards the loop. But if you get kicked off the loop and go inside, you'll go away from the loop. That's called half stable. This is kind of like saddle. In case of a saddle, in one direction you get attracted, other direction you get repelled, right? So this is something like that. Now, why are we giving it a new name? Some of you might be wondering, because in your +2 you have studied something called simple harmonic oscillator. That also gives you kind of a loop behavior, right? And limit cycle also looks very similar. So why are we giving it a new name? How is it different, if it is different at all? Okay, so to answer that question, let us look at the simple harmonic oscillator that you have studied in your high school. So equation is given as d square x by dt square plus omega square x equal to 0. Right, this is a second order differential equation, linear differential equation. But you can write it as two first order differential equations very simply by making this assumption, with this defining a new variable y. So let dx by dt is equal to y by definition. Then you can write the original equation as dy by dt is equal to minus omega square x. So you have transformed the original second order system in one variable. Two first order systems in two variables, x and y. Now these two equations, dx by dt is equal to y, dy by dt is equal to minus omega square x, right? You can see that they are linear equations. It's a linear dynamical system in 2 dimensions, where the matrix A is given as 0, 1, omega square 0. Right now, if you solve for stability of this and find the eigenvalues, you get eigenvalues are plus or minus I omega. That is, they are purely imaginary. So we know from our previous class that when the eigenvalues are purely imaginary, right, you get what is called a center. That is, the system doesn't, the solutions are simply of the form, two sinusoids, right? Not decaying sinusoid, not expanding and expanding sinusoids, but stable sinusoids. So if you plot one against the other, you simply get an ellipse or a circle, depending upon the amplitudes. So if you start from close to the center, you will go in a small loop. You start from far from the center, you go in a bigger loop. But point is, your amplitude depends on the initial condition. Right, you can easily verify this with your simple pendulum. A simple pendulum is an example of a simple harmonic oscillator. If the initial amplitude is very small, you will make a small oscillation. If the amplitude is large, you will make a large oscillation. Right, but your final amplitude depends on the initial condition. Okay, that is the nature of the simple harmonic oscillator. Whereas we can see that in case of uh, a limit cycle, no matter where you start from, you always go to that particular loop. Right? Had it been a center, if you start from here, you'll go in a big loop. If you start from here, you'll go in a small loop. That is the nature of a center. That's the nature of a simple harmonic oscillator. Whereas in case of a limit cycle, no matter where you start, you always go to that particular loop. The amplitude is fixed. Right? So both are periodic, both show oscillatory behavior, periodic behavior. But there's an important difference. A limit cycle is periodic, but it has a fixed amplitude, irrespective of the initial condition. A center is periodic, but its amplitude depends on the initial condition. So there's a very fundamental difference. Now the question is, why should we bother? Right? Maybe we can use either of them. Maybe we'll just use simple harmonic oscillator because it's easy, it's linear. Right? Why should we bother about the limit cycle? To understand neuron model. So the answer is a neuron's behavior is better described by a limit cycle and not by a simple harmonic oscillator. Why is that? So we have seen even in our very first classes that a neuron, once it is excited, it produces a series of spikes. And these spikes, if you plot the voltage, right, look something like this. So voltage increases very sharply and goes to maximum value, comes down and again goes back and so on and so forth. So it's a periodic behavior, or almost periodic. Okay, in this picture, there's small variation here. But the point is, irrespective of the kind of current amplitude that you give, we mentioned that the action potential has the property of all or none, right? If once it is formed, it always has a fixed amplitude. That's about 100 millivolts, right, in amplitude, from minus 70 to about plus 30 and back to minus 70. Not less, not more, right? So no matter how much current you give, if you give more current, it might fire more frequently, but amplitude is fixed. Right, so therefore it is not like a simple harmonic oscillator. It is more like a limit cycle oscillator. Okay, so therefore, moment you start talking about a neuron's oscillation, and a neuron's behavior, once it's excited, it's oscillating. It is producing some kind of a periodic behavior, and it's highly nonlinear, right? And it has a fixed amplitude. Therefore, you need to look at something like a limit cycle. So that's a minimal model that you would need to describe the oscillations of a neuron. Right. So that is how we will motivate study of limit cycles. Now, mathematically, how will you describe limit cycles? So let us look at that. So there are several ways to describe limit cycle behavior in dynamical systems. We'll start with an example. We won't even look at the general theorem. We'll start with an example and see how it behaves. Then we look at another class of systems called Leonard systems. So that means this theorem says that if your equations of certain standard form, right, if the equation satisfies some general conditions, then that system has a limit cycle. Okay, so theorem guarantees it. Then there's another theorem called Poincare-Bendixson theorem, which also says if you can show that your system has certain properties, then the theorem will assure that there's a limit cycle. Then there's also fourth method. What we'll do in this class, we'll just look at the first two, right? And then next class we'll look at the third one. So we'll just start with a special system. We'll write down one specific equation or a pair of equations and show how it can have a limit cycle behavior so that you can get an intuition like how you can get a limit cycle behavior. Then we look at more general cases. So the system we are looking at is given by these two equations. X dot is equal to minus y plus mu into x into 1 minus x square minus y square. Mu is a positive number. Right? You can even assume mu is 1 for simplicity. Right? And we can easily show that this system has limit cycles. It looks kind of a bit complicated, right? I mean, so how do you show that this has limit cycles? The trick here is it looks complicated only in this form. If you change the form into polar coordinates, it will actually has a very simple form. Let us do that. So let's change it to polar form. X equal to r cos theta, y equal to r sin theta. If you plug it in here, then calculate xx dot plus yy dot, this expression. Calculate xx dot plus yy dot. Right? If you multiply x on both sides, multiply this on by y on both sides, add them up. So this term and this term get cancelled. So here you have mu x square and mu y square. So if you add them up, you get mu or times x square plus y square times 1 minus x square minus y square. So x square plus y square is equal to r square. So therefore, you will get mu r square into 1 minus r square on the right side. On the left side, the xx dot is nothing but half of d by dt of x square. Y dot is nothing but half of d by dt of y square. So that will be half of d by dt of r square, right? And if you simplify it further, you get half of 2r dr by dt on the left side. So 2 and half gets cancelled. And r on the left side, r on the right side gets cancelled. You get dr by dt is equal to mu r into 1 minus r square. So this is for the r dynamic. So you are trying to transform xy variables into r theta variables. And the r dynamics will look like this. Well, let us come back to this in a second. Now let us look at theta. Theta is given as tan inverse of y by x. So therefore, if you take d theta by dt, or theta dot, is equal to 1 by 1 plus y square by x square, right? Times derivative of this, that is, in the numerator you have xy dot minus yx dot. In your denominator you have x square. So if you simplify this a little bit, x square gets cancelled and denominator will have r square. And here again, xy dot minus yx dot. So if you take these two, xy dot, okay, that is x times this, yx dot is this, right? So xy dot, so you get basically x square minus, so this whole thing will get cancelled off. You get x square plus y square. If you do xy dot minus yx dot. So this whole thing is just r square. So r square and r square get cancelled off. You get 1. So basically you get, right, theta dot is equal to 1. So you got a very simple form. For r dynamics, it is dr by dt is equal to mu r into 1 minus r square. For theta dot, it is just 1. Okay, let us try to analyze what happens with this. So r dot is equal to mu r into 1 minus r square. Theta dot is equal to 1. So I'm plotting here r dot versus r. Okay, what is happening when r is between 0 and 1? Okay, this r dot is positive. Again, when r is greater than 1, r dot is negative. What does that mean? When r is between 0 and 1, r increases. Right? When r is greater than 1, r decreases because it's negative. So that means at any given point, if radius happens to be less than 1, it will increase and tend towards 1. At any given point, if radius happens to be greater than 1, it will decrease and tend towards 1. Okay, so this equation basically, if you run it, right, no matter where you start, because r is a positive number, so if you start from any positive value, it simply go to 1 and stay there. Okay, so that means the radius of the system will go towards 1 and stay there. So this is about radius. What about the angle? Angle is simply theta dot is equal to 1. What that means is the angle, the system is going at a uniform angular velocity. Okay, so r tends towards 1 and angular motion is simply uniform. So what that means is the system will go to the unit circle and keep going round and round. no matter where you start. So it will look something like this. So no matter where you start, it will simply go round and round the unit circle. Okay, and so this oscillator is actually a limit cycle oscillator because the final amplitude doesn't depend upon initial condition. No matter where you start, it will always go to amplitude of 1 at the unit circle. So that is called the Hopf oscillator. Now I just want to also state that the same analysis, this equations can be expressed also in complex variable form like this. Basically, if you take these two equations in x and y, combine x and y into one complex number, z, which is equal to x plus iy, then you can very easily show that these two equations can be expressed as this. That is dz by dt is equal to minus omega z plus 1 minus mod z square into z. So you can do it as a homework problem. You can try and show that this is same as those two equations. Now you can also express the complex number in polar form. So how do you do that? You say z equal to r into e to the power of I theta. Okay, so that is the polar representation of a complex number. Now if you plug this expression into the first equation, you get dz by dt is equal to e power I theta times dr by dt plus r into e power I theta, right, times I times d theta by dt. Basically differentiating this with respect to r and theta. Okay, so so this is the expansion of this. So equate these two equations. So you get e power I theta into dr by dt plus ir e power I theta d theta by dt. This whole thing is equal to so if you plug in this expression in the first equation, you get I omega as z becomes r into e power I theta plus 1 minus mod z is r, so 1 minus mod z square is 1 minus r square. Z is r into e power I theta, so you get this. So you cancel off e power I theta on both sides. So if you do that, you get dr by dt plus ir into d theta by dt plus I omega r plus 1 minus r square into r. Okay, so now you see that on the left side, this is a real term, this is an imaginary term, this is an imaginary term, and this is a real term, right? So you can very easily separate out the real and imaginary parts on both sides and equate them. What do you have? Dr by dt is equal to 1 minus r square into r, d theta by dt is equal to omega. So now if you take omega equal to 1, like some kind of unit angular velocity, both are just the same. And mu equal to 1 here, right? You get just the same. So the same equations can also be written in complex form. You get this, right? And both give you the same thing, which is the Hopf oscillator, the oscillator which goes round and round on the unit circle. Now in this time in the course, I'll be spending a lot of time on oscillators. So I'll introduce special topic of describing oscillations using complex variables, right? So that's why I want to kind of emphasize that use of description of this in the complex form. So then let us go to linear systems, right? So a linear system is given by an equation of this form. Second order system, x double dot plus f of x into x dot plus g of x equal to 0, which can again be split into two parts. X dot is equal to y dot is equal to, so define y as x dot, then y dot will be written as, right, y dot plus f of x into y plus gx, so that will be y dot is equal to g of x minus g of x minus f of x into y. If you do that, so there are several conditions. I think I'll skip this and I'll maybe cover it in the next class. We'll take some time to explain this. I don't want to rush. Okay, so let me stop here. Right, and maybe we'll do some exercises, right, to understand how null claims work and to understand how stability of fixed point changes. And we'll also maybe simulate the Hopf oscillator to get a feel for how the limit cycle looks and things like that. right? Maybe the next class or the class after on Friday, we'll do some exercises. So any questions? And do you find it too mathematical? Because this is a course on computational neuroscience. It will be mathematical, but if you say something is not clear, we'll change the presentation accordingly and do a lot of examples or whatever. Right? In fact, we should spend some time on discussion because the online class form is by itself somewhat difficult to follow, right? I mean, because you don't see face to face, and so it would be nice to discuss things. I'm open. Like, any questions? Math is fine so far. Somebody is saying Sarvesh. Yes, that's good. Anything else? Anybody else?